Welcome back to G Fun Facts Online, the modern technological renaissance that we are living through right now, spanning everything from the rapid proliferation of electric vehicles to the massive expansion of wind energy and the incredible miniaturization of consumer electronics, rests on a remarkably fragile foundation. I am talking about rare earth elements, lanthanides like neodymium, dysprosium, and terbium, alongside transition metals like scandium and yttrium, are the undisputed champions of materials science. They possess f-orbital electrons that grant them unparalleled magnetic anisotropy, and when alloyed, they create structural metals with extraordinary strength-to-weight ratios. However, this absolute reliance on rare earths has triggered a silent crisis that we need to address immediately. The extraction and refinement of these elements are notoriously destructive to the environment, very often generating radioactive byproducts and massive amounts of toxic runoff. Furthermore, the global supply chain is heavily monopolized, leading to extreme price volatility and massive geopolitical tension. As the world hurtles toward a decarbonized green economy, the demand for these exact elements is projected to outstrip our global supply by tens of thousands of tons within the next decade alone. To circumvent this impending bottleneck, materials scientists are looking away from the exotic and turning their intense attention toward the incredibly abundant. The ultimate solution to the rare earth crisis may not actually lie in discovering completely new elements, but in fundamentally reimagining one of the most common metals on planet Earth, which is aluminum. Through the cutting-edge science of crystal lattice manipulation, researchers are now unlocking advanced aluminum allotropes. These are radically new structural forms of the metal that exhibit physical, magnetic, and electronic properties historically reserved only for rare earths. To fully understand the incredible promise of advanced aluminum, we must first understand the fundamental concept of allotropy. Allotropes are simply different structural forms of the exact same chemical element. The classic example that everyone knows is carbon. Depending entirely on how its atoms are arranged, carbon can manifest as soft, opaque graphite that you use in pencils, or as ultra-hard, completely transparent diamond. The chemical ingredient is exactly identical in both cases. It is the atomic geometry that dictates the physical reality. Standard aluminum, the everyday metal used in your soda cans, kitchen foil, and airplane fuselages, exists in what is called a face-centered cubic crystal lattice, or FCC. In this configuration, the aluminum atoms are densely packed together, giving standard aluminum its characteristic density of 2.70 grams per cc, its famously high electrical and thermal conductivity, and its reliable, easy malleability. It is a highly stable, predictable, and somewhat chemically orthodox metal. But what exactly happens if we force those aluminum atoms out of their comfortable, naturally preferred FCC arrangement? By subjecting the metal to extreme physical pressures, rapid temperature quenching, or by meticulously building it atom by atom on physically constrained substrates, scientists can trap aluminum in metastable states. These are allotropes with entirely different physical, electronic, and magnetic properties. This is exactly where the ordinary becomes the extraordinary. Let us talk about one of the most profound breakthroughs in allotropic engineering, the computational discovery of supertetrahedral aluminum. Designed using highly advanced density functional theory calculations, this metastable phase completely abandons the traditional dense packing of normal metals. Instead of individual atoms sitting in a standard grid, supertetrahedral aluminum is composed of superatoms. These are clusters of 4 aluminum atoms, strongly bonded together into an Al4 tetrahedron. These specific tetrahedra are then arranged into a highly complex, three-dimensional diamond-like lattice, effectively replacing the carbon atoms of a standard diamond structure with entire aluminum clusters. The physical ramifications of this specific geometry are absolutely staggering. The vast amount of empty space, or voids, within this diamond-like lattice results in a material with a density of just 0.61 grams per cc. To put this incredible number into proper perspective, the density of liquid water is 1.0 grams per cc. That means this crystalline solid metal is so incredibly light that it would effortlessly float on a pool of water. Historically, achieving ultra-lightweight metallic structures required alloying aluminum with highly reactive and extremely expensive elements like lithium, or utilizing costly rare earth elements like scandium, just to maintain structural strength at low weights. super tetrahedral aluminum completely bypasses this need entirely. It achieves its extreme lightweighting not through chemical dilution or mixing, but purely through structural architecture. Furthermore, quantum chemical modeling indicates that this specific allotrope is highly plastic and actually behaves as a semi-metal, which completely opens the door for its use in highly specialized aerospace components, deep-sea buoyancy technologies, and advanced flexible electronics. Now, let us move to perhaps the most aggressively pursued holy grail in all of material science today, the rare, earth-free, permanent magnet. Today, high-performance electric motors, like those in your electric car, and massive wind turbine generators rely almost exclusively on neodymium iron-boron magnets, which boast unmatched, incredible magnetic strength. Normal, everyday aluminum is strictly paramagnetic. It does not hold a magnetic field whatsoever. Its 3 valence electrons form a delocalized C, rather than remaining strictly localized to provide the unpaired spins that are mathematically and physically necessary for ferromagnetism. However, advanced allotropic manipulation and controlled nanoscale phase shifts are now actively proving that aluminum can indeed be the key to unlocking powerful magnetism without the need for any rare earths. The secret here lies in deliberately altering the atomic spacing. When aluminum is carefully alloyed with manganese and the crystalline structure is precisely and aggressively controlled, the material forms what is known in the field as the tau phase MnAl. This complex process involves forcing the metal into an Al10 face-centered tetragonal structure. In this uniquely distorted allotropic lattice, the aluminum atoms actively act as spacers. They literally stretch the crystal lattice just enough to force the manganese atoms into a perfect ferromagnetic alignment. This L10 chemically ordered structure yields incredibly high magnetocrystalline anisotropy, which is the exact physical property that makes rare earth magnets so uniquely powerful. While these MnAl magnets were heavily researched back in the late 20th century, before eventually being completely overshadowed by the discovery of neodymium magnets, modern computational materials science is dramatically revitalizing them right now. By thoughtfully introducing new nanostructuring techniques such as severe mechanical milling, rapid melt spinning, and carbon doping to create MnAlC, brilliant scientists are dramatically increasing the coercivity or the strict resistance to demagnetization of these specific alloys. Furthermore, aluminum's vital role in the historic Al-Nico or aluminum-nickel-cobalt magnets is being totally re-evaluated. Al-Nico famously possesses an exceptionally high Curie temperature, reaching all the way up to 1000 degrees Celsius, making it vastly superior to neodymium in extreme heat environments like aerospace generators and deep earth drills. But it traditionally suffered from terribly low coercivity. By applying modern allotropic engineering directly to the aluminum matrix within Al-Nico, researchers are working incredibly hard to pin those magnetic domains much more effectively, striving to finally create a high-heat, high-strength magnet entirely free of expensive dysprosium and neodymium. Beyond magnetism, we have to look at structural superiority and erasing the desperate need for scandium. In the highly demanding aerospace and defense sectors, aluminum-scandium alloys represent the absolute pinnacle of structural materials. Adding just a tiny fraction of a percent of scandium to regular aluminum creates nanoscale L12-ordered Al3SC precipitates. These microscopic, tough structures effectively lock the grain boundaries of the metal perfectly in place, resulting in an alloy that is incredibly strong, highly weldable, and strongly resistant to recrystallization even at very high temperatures. The major problem here is that scandium is notoriously rare, wildly difficult to refine, and prohibitively expensive for mass-market applications. The future of high-strength, rare earth-free metals fundamentally relies on mimicking the exact structural effects of scandium using completely abundant elements and allotropic phase manipulation. Instead of stubbornly relying on exotic elements to form these strengthening precipitates, cutting-edge metallurgists are currently engineering complex stacking faults and localized allotropic zones directly within the aluminum matrix, using incredibly cheap elements like zinc, calcium, and manganese. By subjecting dilute aluminum and magnesium alloys to highly specific thermomechanical processing, such as a process called peak aging followed immediately by rapid cooling, scientists can force the formation of highly stable, non-FCC nanoscale precipitates. These localized, engineered structures behave identically to those expensive scandium precipitates. They act as microscopic roadblocks to dislocation movements within the metal's entire crystal lattice. This brilliant phase engineering yields aluminum and magnesium alloys with true aerospace-grade yield strength and very high ductility, utilizing absolutely only elements that are universally abundant and remarkably inexpensive. Furthermore, ongoing research into aluminum-cerium alloys provides a completely fascinating bridge to the future. While cerium is technically classified as a rare earth, it is vastly overabundant, so much so that it is very often treated simply as waste material during the lucrative mining of high-value neodymium. Advanced aluminum-cerium alloys form highly stable intermetallic structures that completely thrive at temperatures exceeding 300 degrees Celsius, actively replacing the dire need for much heavier cast irons or extremely exotic and expensive titanium alloys in internal combustion engines and high-stress thermal environments. By effectively turning the structure of aluminum into a willing host for the absolute most abundant, otherwise completely discarded minerals, we massively alleviate the crushing pressure on the critical rare earth element market. But the push to redefine aluminum does not just stop at alloys and crystal lattices. It actually extends all the way down to the very core of the atom itself. This brings us to the quantum horizon of semimetals and rare isotopes. Recent mind-bending breakthroughs in advanced nuclear physics have successfully demonstrated exactly how extreme the human manipulation of this element can truly get. Looking at recent data, physicists at the Fragment Separator Facility in Germany successfully observed ALUMI and UM20. This is an incredibly rare, hyper-unstable isotope possessing 7 fewer neutrons than standard, stable aluminum. Lying far beyond what physicists call the proton drip line, ALUMI NUM20 rapidly unravels through a dramatic, never-before-seen triple proton decay chain. While a highly unstable radioactive isotope is obviously not an allotrope, its incredible discovery highlights a much broader, extremely important scientific reality. Our fundamental understanding of the absolute limits of the aluminum atom, from its heavy nucleus all the way out to its buzzing electron shells, is currently undergoing a rapid and profound evolution. This deep, foundational atomic understanding is directly fueling the rapid development of electronic aluminum allotropes. By precisely tweaking the macroscopic crystal structure, we can directly alter aluminum's electronic bandgap. In its standard everyday FCC form, regular aluminum is a brilliantly effective conductor of electricity. But in computationally predicted allotropic forms, just like the supertetrahedral diamond lattice we discussed earlier, it magically shifts into a semimetal. This massive shift opens the glorious door to rare earth-free optoelectronics, highly specialized advanced sensors, and next-generation plasmonics. Standard aluminum interacts very strongly with ultraviolet light, but deliberately altering its geometric structure allows clever researchers to effectively tune its plasmonic resonance directly into the visible and infrared spectrums. This, potentially and realistically, could replace incredibly scarce and expensive elements like indium and gallium in our advanced display technologies, touchscreens, and high-efficiency solar cells. Of course, all of this sounds like pure science fiction, which brings us to the ultimate question of forging the future through synthesis and actual manufacturing. The theoretical existence of these advanced aluminum allotropes is firmly mathematically established, but actually trapping the physical metal in these extremely high-energy metastable states for eventual mass commercialization remains the ultimate engineering hurdle of our time. Because these highly exotic structures are not the element's natural relaxed resting state at standard room temperature, synthesizing them essentially requires effectively tricking the laws of thermodynamics. There are a few major ways scientists are doing this right now. The first method is high-pressure, high-temperature synthesis, often abbreviated as HPHT. By violently squeezing aluminum inside diamond anvil cells, at immense pressures that perfectly mimic the crushing environment of the Earth's deep mantle, the atoms are forcefully crammed into much tighter, highly unnatural configurations, such as body-centered cubic or hexagonal close-packed phases. The massive challenge here is successfully preserving these exotic structures when the immense pressure is finally removed. The second major technique is rapid quenching and melt spinning. By instantly cooling molten liquid metal alloys at blistering rates frequently exceeding 1 million degrees per second, The hyperactive atoms simply do not have the time needed to casually settle into their natural, boring FCC grid. This intense thermal shock literally freezes the material into amorphous states, known as metallic glass, or entirely complex non-equilibrium crystalline structures. The third cutting-edge technique is called molecular beam epitaxy, or MBE. This highly delicate technique involves literally vaporizing pure aluminum and then meticulously depositing it exactly atom by atom onto a specific substrate crystal that has a completely different lattice spacing. The freshly deposited aluminum is literally forced to stretch or compress to match the underlying substrate, severely straining its atomic bonds and growing artificially stabilized, incredibly thin allotropic films. Finally, the fourth and perhaps most revolutionary approach currently being utilized is the heavy integration of machine learning in inverse design. Instead of relying on decades of frustrating, slow trial and error in the laboratory, modern scientists are now heavily using AI-driven computational models to explicitly define the exact magnetic, electrical, or structural properties they desperately want. The powerful AI then works completely backward, furiously calculating the exact required crystal lattice and the highly specific temperature and pressure pathway that is definitively required to synthesize it in the real world. We are truly witnessing the very dawn of the engineered aluminum age. The sweeping geopolitical and massive environmental ramifications of this specific materials science revolution truly cannot be overstated. By aggressively shifting our intense global reliance away from the chemical rarity of the lanthanide series and moving it directly toward the structural engineering of aluminum, which is the third most broadly abundant element in the entire Earth's crust, we are rapidly moving from an archaic, resource-constrained paradigm to a brilliantly intellect-driven one. We can successfully bypass the utterly devastating ecological toll of widespread rare earth mining, strip away the massive economic vulnerabilities of monopolized, weaponized global supply chains, and build amazing next-generation technologies using a metal that is fundamentally cheap, incredibly abundant, and perfectly 100% recyclable. The critical transition from standard FCC aluminum to advanced, highly functional allotropes represents an absolute monumental turning point in the long history of metallurgy. Through incredible breakthroughs like supertetrahedral geometric clustering, L10-phase magnetic manipulation, and highly precise nanoscale precipitate engineering, everyday aluminum is finally stepping completely out of the long dark shadow of its rare earth superiors. As a society looking to an electrified future, we are no longer strictly limited by what the earth randomly provides in frustratingly scarce quantities. Today we are limited absolutely only by our own intellectual ability to creatively rearrange the fundamental atomic geometry of what is already abundantly resting right in our hands. Thank you for listening to this deep dive on G Fun Facts Online, where we always bring you the most fascinating scientific breakthroughs shaping our future.